So the idea was to, if we have an accurate sensor information, just by aligning sensor scans, like laser range scans, we actually get much better pose estimate than comparing just using the odometry information. So what FastLM2 does, it also considers the measurements in the proposal distribution. This kind of breaks a little bit with this clear correspondence from this particle filter implementation to the standard base filter, where you say we only take the control for the prediction step and only take the observations for the correction step. So this kind of mixes those two steps a little bit more together, because it says, okay, we also take into account our observations for already sampling our particles. So we compute a better proposal, and better means here a distribution which is closer to my target distribution. So more samples will end up in the likely areas of the state space, and much fewer samples will end up in low likelihood areas. And this is kind of the key step to bring this algorithm to the next level of performance. So what FastLM2 does, it draws from a proposal distribution which also has all the odometry, all the sensor information in here, right? And this leads typically in proposal distributions which are much more peaked around the true state where the system is in, not these kind of flat, large distributions. So as a result of that, I need less samples, therefore it can be computationally advantageous. On the other hand, I have to say that the computations for this proposal are more involving, and then you may argue that the gain that you get by reducing the number of samples, at least in the computation time you need, may be gone, but you get much more peak distributions, and this leads to a higher likelihood that your filter will not diverge and get good estimates, especially in the long run. That gets more complicated. There's something which is known as FastLM2, which we don't go into the details here for feature-based FastLM, but we do that next week in the context of grid-based FastLM, where we will look into this problem again. Just as a small comparison, how is the performance between FastLM1 and FastLM2? So it's just a small example. Robot was driving around here. This is FastLM1, FastLM2. You see, looks actually not too different the first round. But what you can see is here that these particles have a much longer history, so I have a much larger diversity of trajectory estimates in the past, whereas the FastLM1 down here, if all particles have basically the same estimate, only from this point in time on, they kind of spread out a little bit. And this is the reason that the frequent resampling steps eliminate particles. And if I continue eliminating particles, always a substantial number in every step, I kind of eliminate different trajectory hypotheses in the past, because all the particles are kind of replaced, and then kind of information about the past die out. As a result of that, this FastLM2 has a higher diversity of estimates, because they all are good estimates. Here we just kind of converge to one mode, so to say. This one is more likely to maintain multiple modes, and this is substantially better when you close large loops, or because then multiple hypotheses about how the trajectory looks like in the past make a big difference. But maybe just kind of, this is just as a teaser. We will dive into this into next week, and then you will, let's say, get a bit more knowledge about what's going on, why this is an important property of these algorithms. So to sum up with FastLM, what does FastLM typically refer to? FastLM is particle filter-based SLAM that uses this trick of separating the estimation of the trajectory from the estimation of the map. By saying we use particles only to estimate the trajectory, and then for every of those trajectory estimates, so for every particle, we build a known map. This is something which is called Rao-Blackwellization. And therefore, it's a kind of a Rao-Blackwellized particle filter for SLAM. And using this with landmarks, is Mike Montemello coined this term FastSLAM. And there's FastLM2 and FastLM1. And the main differences between FastLM1 and FastLM2 that FastLM2 uses a so-called improved proposal distribution. So a better proposal distribution which takes into account also the most recent sensor observation in order to have a more peak distribution around the areas of high likelihood. In terms of computational complexity, FastLM is a pretty nice algorithm in the sense that it is logarithmic in the number of landmarks that I have. and linear in the number of samples. And the number of samples is typically constant. Let's say it could be 1,000, could be 2,000, but they are not typically do not grow excessively. Okay, FastLM have been shown to actually work quite convincingly. So it scales very well to millions of landmarks. So there have been data sets with at least 1 million of landmarks using FastLM in order to solve this problem, which gets pretty tricky for EKF, because you would have a 2 by 2 million landmark covariance matrix. You need to invert matrices of this size. It can be ugly. No, you don't need to. That was wrong statements. You don't need to invert them, but you need to multiply those matrices, so you have at least a quadratic complexity that you need to maintain for the EKF. And here we only have a logarithmic complexity, so this is substantially better. Logarithmic is substantially better than quadratic if you compare both. The other advantages of the FastLM algorithm is that you have quite some flexibility in doing data association. You can do per particle data associations, and this is kind of a really nice property and makes it solving the data association problem easier. And it has a further advantage, which I haven't discussed in detail here, but the reason, or the linearization of the motion model, where the EKF suffers from, is not a problem for FastLM, because you just propagate a point through a nonlinear function, namely the pose of the particle. Of course, you still need to sample around that, but it's less critical to have, if you have nonlinear motion models, because you can propagate them in a much better way. You do not necessarily generate a Gaussian estimate. So of course you need to have a way for sampling from these distributions, but you're not restricted to linearization and a Gaussian approach. If you want to know more about FastLM, again, I recommend the Probabilistic Robotics book. In this case, see the errata page, because the printing of the book has still a couple of errors. I hope to have fixed all the errors on the slides here. That's kind of probably the reference which is easiest to grab. Here are kind of 2 papers by Mike Montemello, the 2002 and 2003 paper, where he introduced FastLM one with known data association, the second one with unknown data association, which are really nice works. I guess the first one is easier to grasp, easier to understand, so I would recommend looking into this one. On the other hand, those you find for free on the web. If you don't have the book, you don't want to buy the book, and you don't want to read in the library, you may also have a look to these 2 works. That's it from my side for today. Are there any questions? Okay, good. So we close features for now. It was kind of the last, at least for some time, the last landmark-based approach that you have seen, and we look into the grid-based mapping techniques using raw black-balanced particle filters next week before Christmas, and then also look into kind of this FastLM 2, or kind of FastLM 2 ideas but applied to grid maps, and then we'll have a long Christmas break, and then next year we will look into the graph-based approaches of the simultaneous localization and mapping problem. That's it from my side for today. If there are no any questions, then thank you very much, and we see each other next week. Bye-bye.